Logic depth defines the number of logic gates or the levels between the source and the destination. It can be the longest path between flip-flops within a combinational block. This is a crucial metric in timing analysis because it directly affects the propagation delay and the maximum operating frequency of the design. Logic depth is calculated by counting the number of gates, including or excluding buffers and inverters. Logic depth impacts power, timing, area, and testability. If the design has more sequential elements or a longer logic path, it may require higher drive strength, leading to increased dynamic and leakage power. And a larger logic path also increases path delay, which can violate setup time, and more sequential elements consume additional silicon. However, reducing logic depth improves timing performance, but it may require more clock cycles and increase area due to methods like pipelining and logic duplication. An increased number of sequential elements can also create challenges in testing the design. In static timing analysis, you will compute the arrival and required times between the source and destination points to find the slack value. The path delay is also measured by adding the delay of each gate and the interconnect delay in the path. Therefore, the logic depth directly influences the propagation delay or path delay in the place design with unit delay models. When the delay of a gate in a path exceeds the required time, that path is typically slow and causes a timing violation. However, EDA tools use unit delay models to determine the gate delay based on the depth. Logic paths with larger depth can be targeted for timing optimization through restructuring or pipelining approaches. The switching activity, frequency, and the number of sequential cells affect power consumption. When the logic depth is greater, it requires a lower clock frequency to meet timing, which also decreases the dynamic power consumption. Decreasing logic depth by pipelining might increase the count of flip-flops, which can raise the switching activity, thereby increasing the dynamic power consumption. More logic levels will have higher switching activity with more flops, leading to an increase in dynamic power. And a greater number of gates will contain more transistors, which will also increase leakage power, especially in low-activity blocks. Several methods exist to reduce the logic depth in a path. They are illustrated here. The logic restructuring method modifies or changes the design structure to balance the logic depth across different paths and rewrites the modified design during synthesis. The pipelining approach inserts flip-flops to break long and critical paths in the design. This reduces logic depth and improves timing optimization. During the synthesis stage, the logic in the RTL code can be mapped to faster logic cells in the standard cell library to reduce the logic depth. The depth of logic in the critical path should be minimized first, as indicated by the timing reports. It may also be necessary to swap the cells with faster ones, low threshold voltage cells, or high drive strength cells to reduce logic depth. Here, we will see how pipelining reduces the logic depth of the combinational path in the design. First, a register-to-register path is shown here with a logic depth of 6, which means that 6 gates are present between the two registers. Let us consider the gate has a unit delay. In a situation where these 6 gates in the path have a higher delay, it creates a setup time that is not met, and it results in a higher clock frequency. After implementing the pipelining method by inserting a flip-flop, which splits the long register-to-register path into a path with a logic depth of 3, this minimizes the delay of each stage, helps meet the setup time, and also reduces the maximum achievable frequency. Here is the RTL code for a sample design with and without implementing the pipelining approach. The first RTL code is the design without pipelining, and the second RTL code is the design with pipelining. In the design without pipelining, all the logic operations are performed in one clock cycle, leading to timing issues due to long combinational paths. In the design with pipelining, the operations are reduced to one per stage, shortening the delay and making timing closure easier. In summary, when logic depth increases from a lower value, it reduces the number of sequential cells in the area, but it also leads to longer delays, timing issues, and increased dynamic power. Conversely, decreasing logic depth from a higher value improves timing and reduces frequency, but it results in more registers, higher power consumption in the clock tree, and increased area due to additional registers through pipelining.